Warning: the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is covering, or this video series is covering the mean value theorem, Rolle's theorem, proving when you have existence and uniqueness of solutions to equations. It's actually a really deep theoretical series of videos. And so this is kind of important for calculus students to pay attention to. Obviously, every video in this series is. But we're going to start with one of my favorites, and it's actually a pretty easy theorem to understand. And by the way, this is something that I tell my students in classes, that in calculus, theorems are actually pretty easy to understand when spoken out loud. Like the intermediate value theorem seems like a super simple idea. That's not the purpose of this video, but I just want to draw your attention to this idea. That the intermediate value theorem just says if you have a continuous function and it goes from, let's say, this height to this height, then it must have crossed every height in between if it's a continuous function. So if you started with a function that started at a negative height and ended at a positive height, it had to cross the x-axis if it's a continuous function. Very easy theorem to understand. However, proofs in calculus are pretty much terrible. They're really hard to do sometimes, not all the time. In algebra, it's the opposite. In algebra, the theorems actually don't truthfully make sense if you say them out loud to somebody who's never heard them before. Like if you told somebody who's never heard of the Pythagorean theorem that, oh, if you have a right triangle with hypotenuse C and legs A and B, then A squared plus B squared is equal to C squared. Oh, wow, that's totally obvious. No, that's not obvious at all. So the theorems in algebra tend to not be super obvious, but the proofs are actually pretty okay. So it's the opposite situation in algebra. The theorems are kind of obscure. The proofs are easy. In calculus, the theorems are easy to understand, but the proofs are pretty obscure or can be somewhat challenging. Anyhow, that all being said, let's dive into Rolle's theorem. This video is only going to deal with the concept of it, the theorem, and then the proof of Rolle's theorem, which is a precursor to the mean value theorem. But I just love Rolle's theorem. I think it's such a great theorem. And it's useful in many situations. So let's talk about it. Basic understanding of this very powerful theorem. Let's suppose that you have some function f, and it's continuous from, let's just say from some point A to some point B. So I'll just say that is x equals A, and that last point is for x equals B. Rolle's theorem tells us that as long as that function is continuous on that closed interval from A to B, and as long as it's differentiable, in other words, it doesn't have any kinks, cusps, or jumps, discontinuities, or anything like that. Well, it can't have any discontinuities because we just said it was continuous. But as long as it's differentiable as well, then there must be some point between A and B, and I'll show you one point that satisfies the theorem, that point right there. I'll call that C sub 2. There's some point between A and B where the tangent line to the curve at that point has slope 0. That is, that f prime at some point between A and B must be 0. Now think about it. You have, I didn't mention the most important thing. Oh, no, I did. That the beginning and, I didn't mention it. Okay, so the beginning and end points are the same height. So whatever this height is right here, that's A comma f of A, but that's going to be the same height as f of B. So this is B comma f of B. That's the same height as f of A. That's critical for this theorem. Funny that I didn't actually mention that as I started building it out. But here we go. Let's go ahead and just showcase that it doesn't have to just be 1 point where the derivative is 0. It could be 2 points where the derivative is 0. Notice the derivative is 0 at c sub 1 as well. That's not a requirement for Rolle's theorem, but it is the case in this specific function. For this specific function, it actually has 3 points where the derivative becomes 0. But the idea is that if you have a function and it's continuous and differentiable, and the height at the beginning is the same as the height at the end, or the height at one end point is the same as the height at the other end point of that closed interval, then somewhere in between, the derivative must have become 0, because there's no way to start a continuous differentiable function at a height and end that continuous differentiable function at the same height without reaching a point where you have to come either back down to get back down to that height or up to get back up to that height. So you start climbing, well, you have to go back down to get, let me say that again while I highlight. You start climbing from this point. Well, if the final point is at the same height, then obviously you're going to have to turn that corner and come back down. When you turn that corner, well, you got a horizontal tangent. That is the concept of Rolle's theorem. Very easy concept to understand. And so here it is in all of its glory. Let f be a function that satisfies the following conditions. The first condition is that f is continuous. And that continuous is on the closed interval. It has to be on a closed interval from a to b. The second condition is that f prime exists on the open interval from a to b. Now, let me just address something very quickly here before I continue forward. There is a theorem that we've run into in this course. Differentiability implies continuity. So if you have a function that's differentiable, it implies that function is continuous. However, differentiability on the open interval from a to b does not imply continuity at the endpoints. And so we need that extra little bit of power. We need it not only to be continuous on the open interval from a to b, but we also need it to be continuous at the endpoints. So it can't have a jump discontinuity at the endpoints or something like that. Okay, so that's critical for the proof. And then finally, the last condition, so we have continuity on the closed interval and differentiability on the open interval, and finally, that the endpoints have the same height. Then Rolle's theorem states there must be a number c in that open interval a to b such that f prime of c is equal to 0. There might be multiple points, by the way, just like in that first kind of example that we did, but there's at least 1 point where the derivative is going to be 0. So pretty easy to understand, I think, if you consider this blue dashed line right here as our x-axis, and you said, okay, I got a couple points, one at A and one at B, and I have a differentiable function, and I have a continuous function. Notice those points are the same height. If I start going down, because it's continuous and it needs to get back to that point B, it's got to turn that corner at some point and come back up. Where it turns that corner, it has a derivative that is 0 because the slope of the tangent line there is 0. So that is a really nice theorem to kind of understand. When you go to work with Rolle's theorem, just the same as when we are going to be working with the mean value theorem, you must state to the reader that your function you're working with is continuous on the closed interval and differentiable in the open interval, and that the endpoints are equivalent. If you don't do that, you cannot use Rolle's theorem. Rolle's theorem requires those conditions to be in place. All right, so let's go into the proof. And every proof, you should start with the antecedent, basically the assumptions here. We're allowed to assume that f is continuous on a closed interval a to b, differentiable on the open interval a to b, and that f of a is equal to f of b. When I say f, by the way, I'm assuming that's a function. Now, without loss of generality, suppose that there exists, that's what this backwards capital E means, that there exists a k in our interval from a to b such that f of k is greater than f of a, which is the same as f of b. Now, let me just describe something here because this is an important statement in mathematics. When you hear the phrase without loss of generality, that basically means that we're going to assume something that would have worked had we assumed the opposite. So in other words, in this case, we're assuming that there exists a case such that f of k is greater than f of a, which is the same as f of b. Now let me show you a picture of that. Here's a comma f of a, and here's b comma f of b. Actually, let me write the comma f of a in there, and the b comma f of b in here. What we're saying is just assume there's some point in here where the function is slightly above or significantly above, it doesn't really matter, those two heights. Of course, we could have assumed the opposite. We could have assumed that f of k was below that height. But again, without loss of generality, which means, we could have assumed the other way. The argument would have worked this, similarly. I try not to use that word because it's hard for me to say. But anyway, if we had assumed that f of k was below f of a, which is equal to f of b, the argument would work along the same lines. So let me actually write k comma f of k here, by the way, just so that you have a visual of what we're talking about. So that's without loss of generality, supposing that there exists some number on the number line such that the y value at that number for the function is above f of a, which is equal to f of b. Now, a really interesting point to make about proofs in mathematics is that you want to really look back at all of the definitions. I shouldn't say all of them, but you should look back at the most recent definitions and theorems, relevant or pertinent definitions and theorems that could help you out in a proof. And in this case, we know we have a continuous function on a closed interval. And there's a theorem we learned recently about continuous functions on closed intervals. It's called the extreme value theorem. And the extreme value theorem says, if you have a continuous function on a closed interval, that function will reach its extremes on that interval. It'll reach its absolute maximum and absolute minimum on that interval. So if your function looks something like this, that's not going to be continuous if I do that. So let me, it was supposed to go through there. You get the point. If your function looks like this and it's continuous, it doesn't actually technically need to be differentiable, but if your function's continuous on that closed interval, then it reaches its absolute maximum and absolute minimum on that interval. Okay, so by the extreme value theorem, let me go ahead and pause video and write that. All right, so I've written that out and I've kind of used color to help us kind of visualize what's going on. So by the extreme value theorem, there must exist some point between, or I shouldn't even say between, on the closed interval AB, such that f evaluated at that point, f of c, is the absolute maximum of our function on that closed interval a to b. So let me give you a visual again. So now I have to really adjust this to make this kind of fit the scheme that I'm talking about. So we have some type of function here. It doesn't actually matter what it looks like. It's a continuous function. And let's just suppose it did something like this. Comes back down. It's a continuous differentiable function, but I'm using the fact that it's continuous on the closed interval to say this function must have an absolute maximum somewhere on that closed interval. Now, play along with me for the moment, I am saying that absolute maximum does not occur at the endpoints, and we'll get to that in a moment. But there is some point which is the absolute maximum on the closed interval from A to B. Right there. All right. So now I'm going to deal with the fact that I know that point is not an endpoint. All right. So how do I know that? Well, since f of k, remember, f of k is just we have some number, k, in between a and b, such that f of k is above f of a and f of b. So since f of k is above f of a, which is the same thing as f of b, and we know that we have an absolute maximum at f of c by the extreme value theorem, f of c must be greater than or possibly equal to f of k. Well, because of that, we know that c cannot be an endpoint because k is between those two endpoints and c, or the function value at c, is above the function value at k. So we know, because the function values at the endpoints are below this, I'll highlight it, this guy right here, and that guy could be at max, the absolute maximum, then we also know the endpoints are not going to be what c is. So the maximum does not occur at an endpoint. That's kind of critical for this proof. So we have a maximum not occurring at an endpoint. That's important for us because that means there is, because we have a continuous function, a neighborhood around that maximum. So not only is it an absolute max, but it's also a local max. Now, let me go back to my picture just to showcase what I'm talking about. So again, we assumed that there is some y value, some input value k, that leads to a height above the endpoints. And then, because it's a continuous function, we know that there must be an absolute value between, possibly including the edge points a and b. But we know that there's already a point above f of a and f of b, so therefore the maximum, the absolute maximum, must occur in between a and b. And that absolute maximum occurring in between a and b is critical because that tells us we have a neighborhood about c. And in that neighborhood about c, where our function is defined, all of the y values in that neighborhood are at the height or slightly below the height of f of c. That is, f of c must be a local maximum as well. So not only is it our absolute maximum, but because all of these heights here are locally slightly below f of c, or they could possibly be at the same height as f of c, but for right now, in this picture, they're slightly below. That means we have a local max at c comma f of c. So that's a local max. L max is what I use for that. So notice we're using a lot of the theory that we've developed over the last few videos for the development of this theorem. All right, let's build a little bit more on this. We're actually almost done. There's not much else to say, but I really want to drive the punchline home here. And that punchline is that since we have that f prime exists for all x on AB, and remember, f prime exists for all x on AB because of our assumption here, f is differentiable on A to B, and because we know that f has a local maximum at c, f of c is a local maximum, then f prime of c must be 0 by Fermat's interior extremum theorem. Remember, that was from a previous lecture. It basically said if you have a local extreme, which is exactly what we said that f of c was, we now know that f of c is a local extreme. And if we know that our function is differentiable, and our function is differentiable at that point, then the derivative must be 0 at that point. That's Fermat's interior extremum theorem. So we have actually shown, let me undo my highlighting here. We have shown that as long as we suppose f is continuous on a closed interval a to b and differentiable on a to b, open interval, and that f of a is equal to f of b, then there exists a c, and I'm going to highlight only that because notice when we made that assumption, there exists a c. And we said on the closed interval a to b, but then we later on said, oh, but we know c is not equal to a and it's not equal to b because it is at or above the height of f of k, and f of k is k itself is between a and b. So anyway, that value of c is not including the endpoint. So actually we have said there exists a c in the open interval a to b, and we have shown f prime of that c must therefore be 0. That is a pretty gnarly proof, but a real a good proof to try to wrap your head around as you go through calculus, because you really want to see as many different, there are actually not a ton of different styles of proofs, but you want to be able to get used to the logic behind building a proof. The logic here was, assume what we're allowed to assume, that f is continuous on the closed interval, it's differentiable on the open interval, and that the endpoints have the same height. Start there, and then dig into your bag of tricks, specifically with recent information, because that's how mathematics flows, is that we grow mathematics like a tree, and as it grows, you use the previous growth to build the mathematics. And so I really was only looking very locally, forgive the pun, in our mathematics toolbox for theory that I can use here, specifically the extreme value theorem, because we have a continuous function, and then we use Fermat's internal or interior extremum theorem. So anyhow, that is Rolle's theorem. In the next video, we'll show how Rolle's theorem is actually used.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.